Okay, so hello everyone. My name is Nicolas Gous. I'm part of the inSSIght project, and I will moderate this webinar today together with my colleague Carsten Brockmann and Harald Pötter. This webinar is part of the coordination and support action inSSIght. inSSIght is funded by the European Commission to support the emergence of smart system solutions for different application fields. inSSIght has two main objectives. First, to reflect user needs and requirements and bring them back to the smart systems community. But also to engage with end users and to bring them into the ecosystem of smart systems, to be part of value chains and to increase interactions between technology providers and the demand side. So in the topic of community building and community enabling, we are organizing this a series of webinars. This webinar today is the fourth in a series of collaboration with the Fraunhofer Institute. So today the topic is robust wireless sensing. We have two excellent speakers from Fraunhofer for reliability and microintegration in Berlin. So we have Carsten Brockmann. He's head of group for sensor nodes and embedded microsystems at Fraunhofer IZM in Berlin. He has a master degree in computer engineering from the Technical University in Berlin. And his research interests are on smart systems, of course, particularly sensor network, energy harvesting, low power systems, energy management, but also in this energy application with smart grids, power line monitoring, automated grid infrastructures, and also robust and secure wireless communications. The second speaker is Mr. Harald Pötter. He's head of department RF and smart systems, also from the Fraunhofer for reliability and microintegration. He's a member of EPOS. He holds a master degree in mechanical engineering from the Technical University in Berlin. Following research interests are motivating him, smart systems, sensor networks, and automated factory. So now I will open the floor for Harald and Carsten so that they can start the presentation. So maybe just one precision about questions. You can ask questions using the dedicated feature in the webinar tool. All the questions will be kept till the end of the session, and we will then ask the speakers for the question at the end. So, but please use this possibility to interact with the speakers. So now, Carsten, Harald, the floor is yours.
Okay, hello everybody to the fourth seminar, the fourth technical webinar in the inSSIght project about robust wireless sensing. And Nicola, thank you very much for the nice introduction. And I'm Harald Pötter, that you remember my voice, and that's my colleague,
Carsten Brockmann. Hello everybody.
And we are both working in the field of robust wireless sensing for industrial applications. And what we want to do today is to give you, of course, a short introduction in front of our IZM, but it will be only a very brief introduction. Then we will say what you can expect this day. Then we show a short example that you see how you can realize the robust wireless sensors in an industrial environment. And then we will go in detail to the functional groups of the robust wireless sensor. And we will have at the end a short summary. And then, of course, we will have a common discussion. If you have any questions, please feel free to ask them. Okay, So Fraunhofer IZM, it's a part of the Fraunhofer Society. Fraunhofer Society has several groups. One group is the Fraunhofer Microelectronic Group. You see the figures here. And there are 16 institutes dealing with design, with processes, and with packaging. So Fraunhofer IZM, as Nicholas told you, the name IZM stands for reliability and micro-integration. We are the guys which are responsible for packaging, electronic packaging, for system integration, and as well as for reliability and RF design and sensor nodes. So you see here in the brief, we are starting with our work. Normally, when the wafer leaves the wafer fab, you see the guy with the 300 millimeter wafer. Then we start with our processes on this 300 millimeter wafer. And in the top row, you will see then all the wafer level packaging processes, starting with redistribution. So we bring some wires and lines on the wafer. We will do some vias in the silicon so that you can stack them. And at the last step, we will do the bumping that you can mount then the dies maybe on another printed circuit board or another substrate. So that's the wafer level packaging technology. And the next step, so we have all the technologies in-house for the board, or now we say panel level integration. So we have all the interconnection technologies like SMD, like wire bonding, like flip chip, and other technologies. We do assembly of optical optical components. And as a new technology field, we have the embedding of components into a printed circuit board, and to do the interconnection with the technologies of the PCB fabrication, or we do the mold embedding. That's a new trend now in industry, that you use a huge mold wafer for integration of components. And with all these technologies, we follow our main goal to do the integration of several components, like at sensors, signal processing units, or passive components into one package to have a very dense system. And besides this technological activities, we have two cross-cutting activities. One is dealing with the reliability of the modules, and the others, where Carsten and I are from, do the design. So what happened here? So sorry for that. So if you look at a very high dense package and you think about RF functionality, you have to take the package into account by the design. And that's the reason, because we are dealing with package design up to 60 gigahertz. And to get a better knowledge about the system behavior of our technologies, we are focusing on the system design of smart sensor nodes. Okay, that's in the brief what we do in our department. So we, as I told you, we have the technological departments which need different materials, which develop different technologies. They do the integration of the components, and at the end we will have, for example, a smart sensor node. And we accompany this development by the characterization of the material, by the characterization of the technology in terms of electrical characterization. We do some component design, especially for RF components, for antennas and filters, and we do the system design. And at the end, we will write the firmware for a smart sensor node, and will be responsible to connect such a sensor node to the cloud, to the micro or macro cloud. You will have an example later on. Okay, now robust wireless sensing. So that's three words which we will go in detail during this webinar. So we have the word robust. That means robust in terms of environment of our sensor. This may be mechanical environment, chemical environment, or even the electrical environment. We have the wireless, so all issues which we have to deal with wireless. So wireless means that your sensor nodes will be autarkic. So we have to look at energy issues, of course, for sensing, for processing, and for the wireless communication. And at least we will have the sensor in the wireless sensor node, and we will have a short look about the specification of sensors for wireless sensing. Okay, why we are doing this? If you look here at the Ericsson Mobility Report from 2016, you see that the market growth for mobile phones, for fixed phones, and for PC laptops is still stable. It's a huge market, but the growth which Ericsson and we expect for the future will be in the short range IoT, and that means that the connection, in our case, of industrial devices by a wireless interface, and that implicates what I told you before, that we will have then the restrictions of energy amount, of operating time, and stuff like this. Okay, so what's the design parameters? I told you before that you have, if you look at the wireless sensor node, you have the classical task of sensing, and there you look at the functionality of your sensor. That may be the bandwidth, that may be the clock frequency, but you look at the wireless part for communication range, and of course for the reliability. But because we are wireless and therefore we are autarkic, the power consumption plays a major role in the game, because every of these functionalities like clock frequency, communication range, or reliability has an impact on the power consumption. Higher clock frequency means higher power consumption. Higher or robust communication protocol leads to a higher power consumption. So you have a trade-off between this both specification groups, and of course we'll have the economics. You have to look at the costs. And what we will do in this webinar, we will go to this playing field of contradicting specifications and show how you can come along with this challenge. Okay, we have now one example which my colleague Carsten Brockmann is the head of, and he was the father of this project, and it's now a 10-year, not old, but a story which started 10 years before, and now since 3 years, but he will tell you we have some of the sensors on a real power line working.
Yes, so we would like to present to you the system Astrose, which was built for the overhead power line monitoring, and what we would like to show here in this environment of this webinar is that we had to build up a very robust wireless system, which this system approach stands for, and the measurement task is at least the measurement of the inclination angle of the line. This is due to measuring at least the sag of the line, because it's one of the key parameter for the ampacity of the power line. And beside this, we also are measuring torsion of the line and current flow, and also shortcut, also important parameters for the operation of power lines, and to avoid any risk for the people going underneath, and at the other hand, to optimize the operation and to higher the ampacity. And the application cases or the use cases for this system at least is to empower the grid operators to increase their capacity and to be more flexible, to serve energy to different parts of the country, and on the other hand, to be aware of ice warnings if there are some conditions, environmental conditions, which lead to risky operation, and also other events, for example, a fallen tree into the line, to detect this kind of shortcut or brownfold. So this was the specification or the background where we started to build up this kind of system. And as you can see here on the picture, it's in real harsh environment because the system was to be installed directly on the line. So this means we had to power the device by itself. It has to withstand all the weather conditions around a year, so high temperatures in summertime and also snow and ice conditions and very low temperatures in the winter. And besides this, of course, wireless connection was one of the important tasks because due to high voltages up to at least what we tested, 400 kV, it was not possible to connect any cables for communication on that device. So based on this, we developed a system approach which was based on a wireless robust sensor system installed on the line, here shown as blue colored sensor nodes, and every sensor node then sends its information to the next and the over next, so that we also have built-in redundancy. And at the end of the line, there is a base station or gateway which collects all the information and is able to forward this information to the control center. There are additional components which belongs to the system, a server where all the calculations and data storage is done, and also, of course, other protocols which are able to forward the data into the control system of the grid operator. Besides that, we have interfaces to other external components like weather stations or geoinformation system, which makes the information more powerful for the grid operator to react on any event which can occur. Here we can see on this slide how the system architecture is done for that kind of the system, and what we would like to show with also this slide is how we are on a methodology basis are building up robust wireless sensor systems. So we are relying on a modular approach, which gives the opportunity to change and to modify system blocks and functional groups. And we also can see that we are some main functional groups, which we will also discuss later on in the slides, which are necessary for for such kind of systems. So we see here, of course, the energy supply. We see data communication, wireless data communication, and we see antennas, which are also main component in that system, and we see sensors, for example, for direct measuring of the angle or the torsion, and measuring the current flow. And all these sensors have to be selected to the appropriate measurement task and have to be fitting for the special parameters needed for such kind of the system. And we will see later on how this could be done. At least we have to analyze the information and to show this information to the grid operators. which were then able to perform tasks based on that data, and of course also for analytics to improve the system, to improve algorithms and control mechanism. We need some connection to cloud services, and we need client server architectures to get access to the data. And this is done by that kind of graphical user interfaces. So we are relying on a ribbon-based, well-known look and feel. So we have control elements in the top, and then we can see based on graphs how the system is reacting on the line and how the different measurement values belonging to the weather situation or belonging to other operational things react, and this data, of course, is then analyzed and feed it forward to the control center. To be sure that the system works how it is, how it was designed and is designed for, we started a pilot on that project 2014 and installed 59 sensor nodes on an overhead power line in the middle of Germany in the Harz Mountains, and we have a stable operation since this installation, and this shows that from the perspective of methodology, defining and developing such a system based on that approach is a robust wireless system withstanding all the weather conditions we had, also storm events, and it is able to suffer the energy from the line, and this was one of the big goals which was done here in this project successfully. With the 2 million sets of data we gain each year, we are able to improve the system further on, and we can see how we can redefine or optimize our models for the next development of wireless systems.
Okay, thank you very much, Carsten. So now please remember this example, because we have practical examples later on. Then we will use this example we have shown for the power line monitoring to give you a practical view on the content we try to present to you. Okay, now we come to the functional group. So first, sensing. So there are a lot of sensors for nearly any purpose on the market. I showed you only on the left side above, there's ARMA, a German association for sensor companies, which 450 members, more or less medium-sized companies, and they are offering 198 measure runs and 47 working principles. So it will be very easy today to find a good sensor for your application. But if you go to the wireless sensing, there are some other criteria have to be added for the selection. You have your classical functional criteria, resolution, bandwidth, or offset. You have, of course, cost. But then for a wireless sensor, you have the term size and energy demand. And this becomes, as we told you before, very important. And this narrows a little bit the amount of sensors which can be used for a wireless application. So therefore, we wrote down some rules for the sensor selection. The first thing is I look at MEMS, because driven by the automotive application, MEMS are cost effective nowadays, and MEMS are less energy demanding. So normally you have a MEMS with an ASIC output which uses only a small amount of energy, and that's ideal for a wireless application. And in the next step, you should prefer integrated signal processing with a digital interface, again, due to energy demand reasons. And you should avoid polling and prefer interrupted based architectures so that the system wakes up only if an event will occur. And this is very important to save energy and to lengthen the operation time. And the next step is then to avoid the active sensing principles like heated areas for a flow sensor, like all types of radiation sensors. For example, radar sensors are very energy intensive, or sonar sensors, or even laser-driven sensors. So this principle will lead to very short operation time, and normally in most of the applications they are not good for wireless use. And now you can say, no, that's a problem. What shall I do if I do not found on the first step a sensor which is accurate, which consumes a little energy, and will be fit in the wireless sensor? Then follow this systematic here, and what we often see in our work, that people come to us and say, okay, now I want to measure the pressure in that pipe at that place. And because we cannot reach, for example, in a pump, and therefore just in the near of the pump wheel, I cannot reach it with a normal sensor, so I want to do it with a wireless sensor. And then step back and say, okay, now, because going to this area in a pump with maybe water in it, and to work there for 5 years autarkic is nearly impossible. So you have to step back and then first think about the measurement task and ask yourself or ask your customer, so what really you want to know? What do you want to measure? Is it really the pressure at that place, or do you want to measure something else? That's the first. And then in the second step, if you discuss this, that more often you found that there may be other measuring parameters to measure or to fulfill your measurement task. Okay, in our case, the customer wants to avoid impulsion and therefore under pressure. And okay, then you have to think about what else can I measure to have an idea if, for example, other pressure will occur. It could be noise. If, for example, the bubble will implode, then you will hear it. You have another frequency. So look at these, how you can measure. That's only the pressure. And then you go to the measurement and say, okay, now that's now my principle, how I want to fulfill my measurement task. And then in that step, then you have to think about how I can transform it into electrical signal. And again, there are different principles with a different energy consumption. So as I told you before, one should prefer passive principles, and in idealistic manner, for example, like a piezoelectric working principle, which produces still its own energy. And we have an example later on that you then can achieve very low energy demand, and we will show it later on in the energy management section that will help you to lengthen the operation time. Okay, we have here now two different examples. One now is for a temperature sensor, where you still can see what difference we will have in the power consumption against the performance. And you see here that we have selected different resolution, so discrete steps in the measurement range. And you will see, so if you are asking for a high resolution, it affects your energy demand. So you have a high demand of energy. If you have only low resolution, so it's clear, I think you need only a little energy. And the power from computing is not taking account with this example. That's only the energy needed for the operation for the sensor. So again, if you speak about wireless sensing, so think thoroughly about the accuracy, about the resolution you really need for your task. And now we have another example. So there was a customer who comes to us who wants to have a wireless sensor node for condition monitoring of a machine. So you want to measure the vibration of the machine, and therefore he has a really high outstanding wishes for the specification. And we looked at the different type of sensors, and you see the trade-off between cost on the one side, size on the other side, and again of power consumption and the working principle. So on the left side you see expensive sensor which large dimension, so it's quite large. It depends on the application if that is too large for you or not, but for this application it was quite large, but it has due to its working principle very, very little power consumption and a very good bandwidth. On the other side we have another MEMS acceleration. Both are available on the market, which was very small. So in this case, he fulfilled the needs of our customer at a low price, but with a limited bandwidth and a much higher power consumption. So you see, you have the trade-offs, and you have to thoroughly look at different sensors with different working principles. We have put here some parameter to illustrate that there's all the way the trade-off between energy, between accuracy, between the sampling rate. I do not want to go in detail about this, but it's only for you at home. If you look later on at the slides, you see that there is independencies. You cannot maximize the one. You have to optimize the whole system. Okay, if we go to our Astrose sensor, which Carsten introduces to you a few minutes before, there we were very limited in our energy amount. Even we were on a high voltage power line, we were not able to harvest so much energy. I think Carsten will go in detail to that principle later on, and therefore we were looking for sensors. In this case, we have an acceleration sensor for measuring the inclination. We have a current sensor and a temperature sensor, and here you see the energy demand we have as a MEMS acceleration sensor. This was a commercial available MEMS sensor from the Bosch company, which has a energy demand of 330 microwatt and still contains the digital interface. So all the signal pre-processing and the analog digital conversion is still in that figure, and with we tune them, the sensor, to a low energy consumption. So we had only 8 samples per second, and that goes to that figure with 330 microwatt. And the same with the digital temperature sensor with 150 microwatt in the active mode and only 0.3 microwatt in the standby mode. And we still had the inductive current sensor. And here now, again, that's implication of the sensing principle. So it produces energy, and so we do not need energy for driving this inductive sensor. Okay, we go now to the wireless interface, and now my colleague Carsten will introduce the word of wireless connectivity.
Yes, thank you, Harold. I would exactly like to introduce this figure of wireless connectivity possibilities, and I think this is a good graph to see the main parameter we introduced here for especially autarkic wireless system. The main parameters are the energy consumption, and this is highly related to frequency, to range, and to bandwidth, as Harold showed before. And so I would like to go a little bit through these different protocols. What we see here are the green marked ones, and especially names like Zigbee and Wireless HART, and also Z-Wave are well-known protocols for industrial automation, especially the Wireless HART standard. Zigbee and Z-Wave are more for home automation, but this then standard or protocols based on the standard IEEE 15.4 specially designed for low power consumption and a moderate range, which could be achieved in a line of sight configuration, because this standard is relying on two frequencies, the 868 megahertz and 2.4 gigahertz frequency band, and especially the 2.4 gigahertz band, I will come to that later on, has some advantages, especially in industrial and harsh environments, where we need robust communication. To come back to this special topic of this webinar today, because of course not only communication is some what needs frequency or sending output of different frequencies. Also we have emissions from machines or other things in the environment which can disturb or interfere with such a communication. So there are some parameters which are leading to the right choice of protocols, and this is what we will discuss in the further slides. So to come back, the ISM bands are at the first rule of thumb a good choice because they fulfill the parameters of moderate or low power consumption. They are designed for moderate data rates, which we are finding for application areas such as M2M communication, such for automation issues, or for this example, what we showed here for measuring tasks. And we have a moderate range which could be covered by this system to the next gateway or access point. A special group here at the left corner the ISM bands related to passive RFID, where we can find frequencies from 125 kilohertz to 13.56 megahertz, where we have very low power consumption or power which is also introduced by the reader system. So at least the sensor system itself needs no power for communication. But of course, on the other hand, we have only a low range because we are relying on a centimeter-based distance where these systems are operating, and we have only a very low bandwidth up to 20 kilohertz. But for special applications or if no long distances or high data rates are needed, it could be a very good approach for a very stable system with low power consumption. If we are going more to high data rates, only in a moderate range, we are coming to other standards also well known, like Bluetooth and Bluetooth LE and Wi-Fi, where we have advantages also of standardization and high data rates, but we have more and more also interference with other systems. And of course, what we can see based on the color, we need a lot of power and high power consumption to drive that communication. And so we can say the same for cellular. Here we have the advantage of high or huge coverage, but also we are relying on a high power consumption, which means that this kind of protocols are not well suited for wireless autarkic systems because they could not be served over a long lifetime from a battery or even from an energy harvester. Of course, there might be special application configuration where this could be done, but as a general overview, one can say that these protocols are not really suited for wireless sensor systems. The next slide has a very similar saying, but it's tried to spread the protocols a little bit more into detail so that we can see even special protocols like LoRa or Sigfox, which are here described in a little bit more detail so that we can see what kind of data rate could be achieved. And also, of course, there are application areas or a special application where this even suits best because they have a moderate power consumption and they have a huge communication range, what we can see here on the next slide, because then we are going completely to the right where 30 kilometers and even sometimes more can be achieved in line of sight on the 868 megahertz band. So these protocols could be a choice for wireless sensor system, but on the other hand, the 2.4 gigahertz, where we are a little bit closer distance to the APN, we can achieve, if we go to the slide before, much more higher data rates. We are here in the middle of the graph, and this could be a very good compromise for a lot of application fields, especially in industrial environments. And especially for that application field, we prepared a slide we can see here. So there are some, as I said, emission sources for radiated power. and for example, welding machines, inverter for electrical motors, electrical machines itself for automation purposes, switches and relay, and even induction ovens, what we have for melting. And here we can see what kind of frequencies are the most emissions of these kind of machines in the fundamental frequency and also even in the harmonics. And the main thing here to say is that we are always nearly lying on under the sub-gigahertz band. So this means if we are choosing 2.4 gigahertz communication in the industrial environment, we can assume that we are not disturbed by any radiated emission sources. And we have the advantages that is a good acceptance worldwide, because this is an ISM band which is worldwide license free and mostly standardized. But of course, as Harold introduced, we have some competing parameters, and there are also applications thinkable where the choice of 2.4 gigahertz is not a good choice. For example, wet environments, if there are some liquids where I would like to communicate through 2.4 gigahertz or even higher frequencies are not the best choice. Yes, and coming back to one of the main parameters designing such kind of systems, it's of course the energy. And what we can see here is a complete graph of a periodically operation of a wireless sensor system. And of course, the communication here at the end of the graph is one of the most consuming sources of the system. So this means a good choice of the communication protocol, and even also the architecture of communicating. This means also data reduction, topology, and things like that is necessary to develop and to simulate before build such kind of a system to achieve lowest power consumption for robust operation, and especially for energy autarkic operation. And this is also a motivation slide for the next upcoming slides based on energy and power management, because as we can see here, it's not only a problem of the power consumption by a mean value, it's also a problem by consuming power in the burst modes. So we have here to adapt the source and also even the load together to achieve a best efficiency of power distributing in the system. Yes, and so we are directly in the energy management. The main tasks are to ensure proper functionality of the main components and functional groups in the system. And as shown in the slides before, these are sensors. This is mainly the communication, but also data processing, network coordination, and even self-test and diagnostic functions, and all related to alarm functions, which has to be ensured for a robust system operation. Because if I have an event, for example, here on a high voltage power line, which should immediately lead to an alarm, and I have no reserves on the power or energy storage, this will lead to a failed function, which is necessary for that kind of device. And this at least will lead to a fail function of the whole system. How energy management could be done for this system, we introduced several tasks, and in the past we developed several tasks. And here in the top we can see that we have different steps in doing some kind of power management. There are several components which are interacting. The first one, of course, is the energy source, which can be an energy harvester or which can be a battery. And then, as I said, we have to match the impedance of this kind of load to this kind of source to the load of the system. And we need for that storage of energy, conditioning and distributing. And what we introduced or what we like to introduce here is not to do this on a steady state approach. We introduce here a dynamic system which lives from a control loopback where we know several energy parameters of the system, and with this parameter we can feed an impedance matching network so that we can introduce algorithms like maximum power point tracking, or we can introduce quality of service algorithms which lead the system to lower special functions to a minimum of service if the battery goes down or if the harvester is delivering not as much as energy it is needed by the system. A further task is managing multiple energy sources, especially for a robust wireless system. One should not rely only on one energy source, especially if it is an energy harvester. There are several architectures and approaches on the market, but what we would like to introduce here is a multiple energy source which automatically switches over between several harvesters and backup battery, which then could maximize lifetime. If we have enough energy from a harvester, for example from a solar cell, we can suffer the system directly from that kind of harvester. And if we are losing power from the harvester, we can switch over to the backup solution to ensure proper operation of the system. And the next task here is a little bit more detailed, what I have already introduced, to bind also information on the power management from the several functional groups, such as wireless communication, also from the MCU load. If we have high performance data calculations, or if you use complex sensing algorithms, we can then feed back this information to the power management and to adjust power conversion and energy use. And this slide should show what could be done by the system itself. So it's based on a high configurable system approach. For example, that modules can be shut down during operation, or another algorithm is dynamic clock scaling, so that different peripherals inside the MCU, also inside the system, could rely on different clock domains. And based on what I said, the information of the different components, we can adjust highly degree on a high granularity basis the clocks needed for each of the module, and so we can adjust energy consumption on the whole system. To know at the beginning of the development phase what kind of energy I need for ensuring operation of the system and what functionalities I have to build in for the power management. It's necessary to know what kind of energy I need and what kind of energy I have based on environmental conditions. And for that, it's necessary to calculate on a periodically basis to have an average value what kind of energy I need for the system. And I can say here for the Astroza system to say that in the early time we have not as much as energy one can think from a high voltage line, because we are relying not on an inductive approach, because power lines are not always running on 100%. They are at the most time running only at 5-10%, and sometimes also switched off for maintenance reasons. And so inductive harvesting also at power lines is not even the best principle to ensure a robust operation at this time. And to know how many energy I need and how or what kind of principles I can use for such kind of device, it's necessary to do this calculation. And I will show this on the next slide. Here it's a model based on average building values at a regular basis. And what we can find here on the left side in the red colored box are the main functional groups which are already introduced. So we have sensors, for example, the acceleration sensor, the temperature sensor. We have the communication components like the transceiver, which is already introduced here, based also on a 2.4 gigahertz communication. And for example, we have an additional component like the RF amplifier. And of course, we have also take into account that the energy management itself needs some energy, because we have not a 100% efficiency system. There are some losses due to leakage current or to conversion losses. So this has also to be taken into account. And at the end of the day, we come to an average sum of 4 to 6 milliwatts for that measuring system based on a 15-minute interval, altogether with sensing, with communication, and with data calculations and measurements.
Okay, now I think we are now at the end of our time, so we we prepared some about energy storage and harvesting, and I think we can skip this. I think that's only one figure to show you why we are naming energy all the time in every second sentence, because there's a gap between the energy density of a lithium cell on the one side and the power density of, for example, in this case, it's only, for example, Intel i7 processor, and that makes it obvious where the gap is. If you look at the lithium cell, and that's a good cell we have selected here, it's around 2000 watt seconds per cubic centimeter. And if you look at the power density of an Intel i7 processor, that are 264 watt per cubic centimeter. So if you would have the same volume of both, that's important. It's I think it's 4 processors you need for that volume. Then it needs not longer than 10 seconds that your 1 cubic centimeter lithium cell is used and empty. And that's the background of why energy is very important for all these types of robust wireless sensing. So I think you will get the slides later on, and if you look at the slides, you will find some some information about batteries and energy harvesting and what the problems there are and where you have to look by if you select the battery. Now I think we are at the end, and Nicolas, maybe there are some questions.
So yes, thank you, Harald. Well, for the moment, there's no question from the attendance, but the participant can still ask some. So if you want to ask the speakers, please do so. Well, we will wait maybe some seconds. In the meanwhile, I would like to thank you first, Harald and Carsten, for this very nice presentation. Yes, there's okay. It's more a comment from Petra Weiler. Just to mention that we have now actually within EPOS, within the European Technology Platform on Smart System Integration, we do have a working group working on the aspect of energy. And what you presented, Harald and Carsten, is also part of the discussion that are taking place in this working group. So that's good to mention that EPOS is addressing the aspects of the application of energy. So thank you. Well, yes, we don't have other questions. Okay, if it's so, well, again, thank you very much for the presentation. As you mentioned, um, the slides, well, actually not directly the slides, but the webinar is recorded. So the whole thing, so the slides plus the voice will be available in a video afterward. We would make that available on inSSIght website. So that anyone can have a look at that afterward, or even if you didn't not attend, you can also send the link to colleagues so that they can have the full webinars offline. And then, yeah, before closing the webinar, I just would like to announce the next webinar that inSSIght is organizing. That's basically next week on the 20th, in 1 week at 1:00 p.m. We do have a webinar not on these topics, but on artificial intelligence. So the title is Do Not Dream, Artificial Intelligence Will Not Solve Everything, with actually the impact of artificial intelligence on semiconductors, also on the topics of energy with smart grids and from my colleague Stefan Wolf. So you can invite it to join the next webinar. Yes, so basically that's it from our side. Thank you, Harald. Thank you, Carsten, for the nice presentation, and thank you to all participants for having attending this webinar. Thank you very much. Bye bye.
Okay, thank you very much, and thank you very much